We will start in a couple of minutes. Hello, everyone. I'm Rafiq Mitri, Technical Marketing Engineer at Mouser Electronics, and I'll be your moderator today. Thank you for joining us to Mouser and Texas Instruments webinar, Develop Your Functional Safety Signal Chain Application with Texas Instruments. With 50,000 Texas Instruments parts in stock available for quick delivery, Mouser is a global distributor of the newest semiconductors and electronics components from over 1,100 manufacturers. Throughout this webinar, there will be several polls to help the presenter tailor the content as we go along. Please ask any question you may have on the presentation using the Q&A button below, and we will answer as many questions as we can at the end of the presentation. If you have any technical questions around audio or webinar functions, please use the chat function and someone from the Mouser team will help you as we can. Without further ado, I will hand over to Lars.
Thanks a lot, Rafiq. Thanks a lot. Welcome to my presentation, dear audience, to develop your functional safety signal chain application with Texas Instruments. So within the next 40 minutes, I actually want to show you how a functional safety development flow can look like, or at least this is the process I used. And let's see how this works with the agenda first. So first we look at the scope of our subsystem. What we actually do is we develop a subsystem and we show also the parameter of that subsystem. Then we go straight to the concept, which is the first important part in the functional safety flow, including the block diagram and the concept FMEDA. And then we go straight to the realization, which includes a sample schematic, a sample system FMEDA, and finally the results. And the third section, we will have a closer look to some diagnostics I selected, so you can actually understand how what I thought when I actually wanted to reduce the undetected faults, for example. So the entire project was created together with TÜV Süd. So I worked with them and provided some material, for example, the technical report on the concept, and also the safety manual, which actually describes all the surroundings and the requirements for the surroundings of the subsystem, and the FMEDA, the schematics, and finally also hardware description, which talks in detail about the implementation. The scope, as you can see, is in the red box. It's an analog front end consisting of 2 channels. which is embedded in our example in a 420 milliampere current only analog input module. So this is a quite common functional safe module, current only input module. We don't talk about the protection. We also leave the processing and the power out, but we will really take care of the analog front end, actually digitalizing the analog input to the digital output. So you can see on the safety relevant parameters, we want to reach up to CO3 according to IEC 61508. According to ISO 13849, we want to reach a level of Cat3 PLE, and this already asks for a redundant channel architecture. So that's also the reason we have this 2 channels here. We were choosing a 1 out of 2 architecture, and this directly means we have a hardware fault tolerance of 1. So this means we can allow 1 fault and still can bring the system in a safe state. So we have a tolerance of 1. The diagnostic test interval is 400 milliseconds. So all diagnostics performed here will run within the 400 milliseconds. The demand mode is continuous, and the proof test interval is 20 years. Regarding the actual I/O or the input parameters, we have 6 input channels independent. Input type is different. So this means we can allow a common mode voltage here as well. The input current is 420 milliampere. As you see it a lot in the functional, in an industrial environment with field transmitters, we have an input impedance of more than 100 milliohm. The resolution given by the A/D converter is 16-bit, where the 8 MSBs are the 8 safety bits we take care of, basically. The update channel rate is 400 milliseconds if all the inputs are on, and the maximum error is 0.4% maximum over temperature. The mains frequency rejection is at least 78 dB for the 50 and 60 Hertz. And finally, the operating temperature, ambient temperature is -10 to 60 degrees. So now the concept. Everything starts with the concept block diagram. But before I come to the block diagram itself, let me explain here this table. This table shows the relation between a certain seal, a hardware fault tolerance, and a safe failure fraction, the SFF. So you can see clearly we have 2 channels. The 2 channels, channel 1 and channel 2, they are the same. And we have a common element diagnostics. So it is useful to split all the logical components into elements in such a concept block diagram. So we decided to go for the element analog input, element data conversion, and element communication. The analog input has some sub-elements, but I mean, it's free for you. You can also split them into separate elements. So you have a longer chain, no problem. I did it this way. The analog front end is included in the analog input, the external multiplexer, the INA for common mode rejection is inside here, and an I/O expander for the channel selection of the external multiplexer. The element data conversion is basically the A/D converter. It has an internal multiplexer in PGA, an ADC in filter, logic, an internal reference, and the clock. And the element communication, the last element of the channel, is basically the communication to the outside, to the microcontroller or microprocessor. So now, as we said, we want to achieve a CL3. So we basically work in this area here. And with the hardware fault tolerance of 1, which is here, we actually identified the column we need to work in, right? And here you see a B and an A. What is that? Here you can see A is a type A. We talk about the elements, we're the components at the end. Very simple components are, for example, resistors, capacitors, inductors, but also small pin count, low transistor count semiconductors, op-amps, references, comparators, you name it. These are also still type A elements. The type B elements are the more complex elements where not all failure modes are well defined. So with the type A elements, we can exactly say how these elements can fail if they fail. With type B elements, we cannot take this assumption for all the failure modes. So now back to the application. You see the element analog input, actually put it in an arrow here, has only A elements. This one, so all these elements are A elements, which means we need a safe failure fraction for this element of 60 to 90% or more than 60%, as we normally say. For the element data conversion, this one, which is, as I said, the AD converter, which is rated a complex element, we end up here in one level more for the safe failure fraction, so we need more than 90%. You're sometimes also here low, medium, and high coverage. So we are in the low for the A elements and for the B elements in the medium. So now the element diagnostic is a special one. How to rate that? So we know we want to have the CL3. So, and the diagnostic is always one seal level below. So we actually play in the CL2 area. Now that we have a redundant channel architecture, so we have a 1 out of 2, we can deduct another seal level. So we end up with our diagnostic element in the CL1 bucket. And now if we can actually manage that our diagnostics are all A elements, then we would have here a single diagnostic without any further diagnostic. So if I would have, let's say, a diagnostic element, a single one with B elements inside, I would need to test the diagnostics, most likely. But since, and you will see this later, we have in a diagnostic element only A elements, we are easy. We do not need additional diagnostics. But if you decide, for example, to add a deck, for example, to test your AD converter, to set certain voltages, then you have the options to have a per channel diagnostic without test, or you do a common one with additional tests. So then the next point is that we take our IEC 61508-2 table 1, and we can now map our B and A elements into the different columns again. So we play in the discrete hardware, and you see for the low, which means our type A elements, we need to test against stuck-at faults, and only at stuck-at faults, or zeros or ones, or one at the pin of an element. So, but for the AD converter, for example, we do the medium, 90%, and here we have to test against also stuck-at faults, but also stuck open or high impedance outputs, short circuit between signal lines, and for integrated circuits, short circuit between any two connection is considered. So if you have a 100 pin device, you actually need to check against all the combinations. But with our redundant channel architecture, we have an advantage here. So stuff gets a bit simpler. Now the next is the concept FMEDA. This is basically another table which makes a qualitative assessment of our elements. We see here the element again, data conversion with the multiplexer, PGA, ADC, and filters, so all what we saw before. It's a type B element. It has a certain function. The function of each sub-element is here described, and also the faults, basically what can go wrong. Impact on safety function, definitely. So if the AD converter breaks, you cannot make sure that the output is really what the input is. And then we need to find out how can we actually, we need to add a measure to control or detect the fault. At the end, for example, for the clock generator, right? You have generates the clock. It has an incorrect frequency or no clock. This could be a fault. The measure to control or detect the fault can be measuring of the duration of the conversion, or also a channel comparison, and the resulting requirement, for example, for the connected microcontroller or microprocessor, is a mechanism to measure the conversion time. We will say a bit later in the diagnostic section how this can be accomplished. But here already, TI can provide you information about the faults. So we do have information publicly available, which actually shows you for certain components, all the failure modes. Now, let's come to the realization. We did our concept, we finished the concept, we have our block diagram, we know what to do, we identified the failures. Now, let's put it into real stuff. Here's the schematic top level sheet, where you can see the analog front end. Here's the signal chain, another one, like the lower one, and here you have the diagnostic, which is common to both. So they are connected to both in the same way. And then the interface, of course, the power and the processing unit. So this is the schematic of one channel. So one channel consists of 6 analog front ends, which is basically our shunt and an anti-aliasing filter. These 6 channels go into this 2-channel, 8-channel but dual multiplexer, the MUX 36D08. But you can also now replace that multiplexer with one of the fault-protected multiplexer from Texas Instruments. So if you have an overvoltage here, you do a search or whatever, they are also effectively stopped. Then we have the signal, the selected signal coming out, going to the INA 826, which is basically taking the differential signal and putting it to a single-ended, converting it to a single-ended signal. And this is then directly feed into the A to D converter. The A to D converter is the ADS1119. I choose this A to D converter, this delta sigma converter, for multiple reasons. So first, I needed a multiplexer with 4 inputs. This was good. I needed an A to D converter with an internal reference, also important. And I also wanted a very simple, not very complex device in terms of registers. We will also say later that it has advantages to have maybe only 1 or 2 configuration registers instead of 20 or 30. So this converter was just right and talks with I2C to our processing unit. Also connected to the I2C is the TCA 9536, which is a 4-pin GPIO expander, and this controls the lines, the channel selection lines of our multiplexer. And then we have some resistors here, and I will talk about them in a while because they're helping us on the diagnostic already a bit. But the diagnostic itself is quite simple. It's really consisting only of an external reference, the 1.25 volt reference, some resistors to create test voltages, and then also an TMP235, which is a temperature sensor, which measures the environment, the ambient temperature, and senses the analog output, the presentation of the temperature in the analog voltage to the AD converter, so that the AD converter always knows if it's working in the correct temperature range. Now that we have our schematic, we can come to the FMEDA, to the part list. So this is actually an Excel list which has all the components, all the schematics from the schematics. So you see we have a position, we have the amount. So for our analog front end, for example, you find the shunt resistor 0.3, for example, the shunt resistor 6 times. You have a small description, but I only put the description for the ICs here. Then what is it? The resistor, capacitor. Then we have the reference. So we actually want to find our device in our schematics, right? We have a housing and a short description. What does it do, this particular component in your system? Then we have the block number and the block name, which is basically our element from the block diagram at the beginning. And then we have, this is the first time we meet the failure rates, the fit rates. So for example, here the resistor has a 0.2 fit, 1, but since we have 6 resistors here, it's a 1.2. And this goes all the way, and you can see here already the analog front end itself has a fit rate. And I'm not talking about dangerous or not dangerous or safe failures, just the normal fit is almost 125. For the data conversion, it's 45, which is basically, as you can see, only the ADS 1119 and 2 bypass caps. And then we have, for the communication, we have basically a lot of resistors. It's a 1.6 fit rate. So, Julia, I think now it's time for our poll. So we actually prepared one question for you, and we'd like to ask you to answer this question within the next minute. And in the meantime, I can actually express a bit more about the fit rate. So the fit rate can be, I can generate your fit rate basically. So if you have a question on a certain component and you don't find any function safety information about this particular component you want to use, you can talk to your sales representative from Texas Instruments, and he can provide you the information. For the non-TI parts, so for the passive parts, I can really recommend the book. I get also the recommendation here for this book. This is called Reliable Engineering. It tells you the fit rate for the passives, so for the R's and the C's, also the failure mode distribution and failure modes. So I think it's a very, very good book, and I enjoyed it quite a bit. So we actually, for this application, we used SM29500, the Siemens norm, to calculate our fit rate. And we need a small adaptation because we have now a constant ambient temperature of 60 degrees. So this is also already in the fit rate we provide here. But of course, the IEC 62380 is also another standard you can use, but you have to choose one. Either the SM29500 or the IEC 62380. You cannot use both in your application, in your circuit. Both have their advantages and disadvantages, but I think, it would take another 2 hours or so just to talk about the differences about these two standards and when to choose what best. So in the meantime, thank you for your participation. In the meantime, we have a result, and 60% didn't know. So, it's bad, but it's also good, because then I can also show you where to find all these data. So in the next slide, this one, we come to our sample system FMEDA table. So another table. Yes, another table. This is a bit different from the concept FMEDA. now we really go into the numbers, right? So we have again our analog to digital converter here, for example. We have a base failure rate, maybe you have seen this in the last slide, of 41. So 41 failures in time, right? Then we can actually, we see our failure modes here. These are all the failure modes which can happen. I mean, it can be more, but this is what we at least state. And you have, for example, a channel-to-channel short, incorrect channel selected for the multiplexer, right? ADC output code bit error, ADC gain out of spec. I mean, all these certain failure modes which are common to an A to D converter. Then you have a column where you can see the failure effects on component level. So for the component, this means if I have a channel-to-channel short, I have a mix of two different input channels. Yes. And on system level, this can mean the input to the A to C does not reflect the inner output. So the inner output, you remember, the op-amp, which provides the single-ended signal, feeds into the multiplexer. But if the internal multiplexer to the A to D converter has a short with another channel, then what's coming to the modulator is not what the inner sent out. This is actually what it says. So then we can do the diagnostics here. We can short detectable with test voltages, for example. And so we have the certain diagnostic matrices here, output comparison. Then we have to say, is it a dangerous error or is it a safe error? But since it's our A to D converter, it's a dangerous error. So any fault into this, or a fault into this A to D converter can result in a wrong result. Then we have a fraction, the failure mode distribution. So the channel-to-channel short has a likelihood of 10% out of all failures of the A to D converter. This means that the 41 fraction is 10%. We have 4.1 dangerous errors. And this leads to, they are all dangerous, of course, but our diagnostic coverage, and I'll talk about this a bit later, is already 99% due to the redundancy of the channels. So the redundancy of the channel is a great vehicle, and this reduces our dangerous failures to only, or dangerous undetected failures to 1% only. So this means we have here our 0.04 fit rates, which are still dangerous and undetected, whereas the vast majority of this error of the 4.1 is now dangerous detected because we can compare the two channels. And at the end, we apply this to all. They are all 99% in our case. So this means out of the 41, only 1% remains, which means 0.4%, 0.4 is the fit rate of our A to D converter. And believe me, if you have a single channel redundant, if you have a single channel architecture, you have to do much more in terms of diagnostic and to reach such levels, right? So for the 60% who don't know yet how, or who didn't know that TI provides such information, I really want to show you real quick how you actually find the information. So first you go to the ti.com page. When you press then here the application section, there's a new window coming up. And here under technology, you see functional safety. And if you press the functional safety button, then you come directly to the functional safety landing page. And here you can read about all the information and also about the categories. So TI introduced already 2 years ago 3 categories from functional safety capable to functional safety quality managed and functional safety compliant. And you can see that on the functional safety compliant, for example, you get all the information. So this is really, the device is developed after the functional safety process. So there are assessed, for example, by TÜV. So So you can very simply use them for your function safety application, but of course still you need to assess your final application with TÜV as always, or with any other certification body, others like EXIDA, for example. Then we have also, and this is special, function safety capable. Here we actually provide information for standard products, for example, comparators, ADOs, right? So we thought this could be an interesting component for our customers. And now we actually generated some function safety information like the fit rate calculation or the FM with the failure mode distribution and the failure modes, right? So, and this is already something you can use for these tables. And this is what we provide for selected components. And more down this page, you can find all the components with functional safety category. But if you are in a standard product list, you can also enable the header TI functional safety category. And then it says directly if it's safety function safety capable, for example, or it has no information. And if you click then on this part, you go to the product folder, and then you can already find a document which has all the information. So then coming back to our application, the results now after the calculation is 7.66 fit rate. We say, wow, 7.6 is already quite a bit. That's right. But it's important to understand that this number was taken with a very conservative common cause factor. So as you know, the common cause factor is plays a very important role in a redundant channel system, in our 1 out of 2 system, because we need to avoid that both channels are influenced by environment or so the same way. So we heavily, you will see that you heavily rely here on the comparison of the 2 channels. But if the 2 channels drift the same way in one or the other direction, the comparison is still the same, and you have a problem. You still get the wrong error, but you do not recognize it. That's why the common cause failure is very important. And since this is only a subsystem, so I don't know anything about the application. I don't know if the 2 channels are on one board or if are they maybe 2 meters apart. I cannot tell. That's why I need to say I take a conservative common cause factor of 5%. And here with this one, I end up with 7.66 fit rate. But I did the math for 1%, for example. And for 1% common cause failure, I was able to reach 1.5 fit already. So this is just to get you an idea how important the common cause failure assessment basically is. And this is also the reason here why I have the common cause failure of 0. I didn't populate this table because I didn't know. That's why the calculation, the common cause failure is 0, or it failed at the end. And this needs to be determined later by the system integrator. The system integrator has all the information about common cause factors, and the subsystem we are discussing here is then at the end just a part of the entire system. So now I think this is the third sector of our presentation here. This is the diagnostic review examples. I mean, there are a lot of diagnostic examples. I just picked some important that you get an idea what I did here. So the first is, I would say, the most important. This is the comparison of the conversion result. I cannot stress the point enough what advantage such a redundancy has, right? So the default is a random fault in any channel. So if there is a random fault in any channel, we may figure that out with our comparison in the comparator or the microcontroller microprocessor. So at the end, we get from the same channel, we get our information, our code, our output codes, feed it to the controller processors, and they compare. And if the comparison is good within the range, then you have already quite a good idea that everything works as expected at the end. Only the 8 MSBs are important, right? The safety relevant bits, and we can already get a DC of more than 99%. So the standard, it says we can reach with this measure already 99%. And here I copied the text from the standard. It is a data flow dependent comparison of independent inputs to ensure compliance with a defined tolerance range. There will be a 1 out of 2, 2 out of 3, or better redundancy. This measure is only effective if the data flow changes during the diagnostic test interval. What does it mean? So imagine you have 8 or 6 channels connected, and all the 6 channels, they get 10 milliamp. So you can switch between the channels, you still get 10 milliamp. How do you know that, that the entire signal chain still works? I mean, this 10 milliamp can stay forever, right? So you don't know anything about the vitality of your system. And that's why we need to change data within the diagnostic test center. But as we do additional tests, you can see later, we will definitely change the inputs and outputs. So this is already given by the hour diagnostics. And you can also see this, what I forgot to mention before. You see also the stacking of the 2 channels. So the current for the 20 milliampere loop comes in here, goes up, goes through the shunt, goes down here to the second one, and goes back to ground also. And here you can see that the current of both channels is the same, basically. So the second one is the ADC output code bit test. Very important and also very hard to handle. The output code bit, so you have to make sure that the output codes are still toggling, are still valid. How can you do that? So imagine again the 10 milliamp and nothing changes here, and you want to see if your MSB is really still toggling or not, but you cannot tell because the input is just not like this, right? So that's why we create a test signal with the help of the external reference. So here's our 1.25 volt reference, which is connected directly to the external reference pin of the AD converter. So the AD converter uses now our external reference. And then I take this quite precise resistor divider. And this is a 2/3 resistor divider. So the bit test voltage here, as you can see, is 0.833 volt out of the 1.25. And the voltage is here feed into the A-in-1. And this means we have a ratiometric measurement. So the voltage source of the external reference and also of the bit test is same. So if there is if the reference is not as accurate as the it's not accurate, for example, then the external reference and the bit test goes the same way and it cancels out the error, basically. So, and in order to get actually the 010101, we need this voltage of 2/3 of the reference. And the good thing is that if you want to also test the 1010, so you want to flip all the bits, we just negate the differential voltage. And this is what can be easily done within this AD converter. So for the 2/3 of VREF, we have A-in-1 connected to the positive and A-in-0 to the negative of the input of the AD converter. And for the second, we just flip it around. And so we didn't do anything except changing the multiplexer. And now we have 0 1s or 5555 or AA. And with this, we can test all the bits. And also we can see if there are some influence of adjacent bits. So once maybe one bit tends to do what the other bit does, the neighbor bit, and this can be also addressed within this diagnostic. The next one, the diagnostic 3, is the external MUX and the ADC MUX. Here we want to test the channel stuck on, which means we want to see if any of the channels stuck. So what could happen is that one MOSFET, for example, one switch doesn't open again, right? It, for example, let's assume A in, A0, so the first sensor channel is always stuck on. How can you actually figure that out? So that's why we have the resistors here. So all the inputs to the multiplexer, to the external multiplexer, have a certain resistance. And with that, we can, while we're testing our test voltages, we can figure out that something is wrong. We do not really need to know which channel is broken. We just need to see there's a channel broken and we can react accordingly. So, for example, if you have stuck here and now you have the resistance, which is provided by R1 here, for example, right? It's the same resistance as R4. And at this point, you will have then a resistor divider. If you select this channel and the other channel stuck, you have a resistor divider, and you will not be able to measure the test voltage again. So this means we would expect all the time for the channel 0 here, for our test channel, a 0 at the output, because they are both connected to ground, right? This would be a difference of 0. This would also mean a difference of 0, and that's it, 0. But if it's not 0, we know something is wrong. In the unlikely case that here is a 0 voltage, it could be because of the common mode voltage, right? It could still be this one can be 0 or this can be 0. Then we would figure that out by sensing the second test voltage, which is S8. This is actually a 0.4 volt test voltage here. And this would actually not be measurable if there would be one channel stuck ground, for example, here. This would also, you could also figure that out in all cases. For the ADC multiplexer, I use a different method. I just said no internal voltages can overlap, right? Here the temperature voltage range is in 1.6 to 2.3 volt. The bit test voltage is 0.833 volt, and the sensor input voltage range is from 90 to 452 millivolt. So if I get some voltage in between, I know already there's a problem, there's a stuck. So I use two different methods for the two different multiplexers. The diagnostic 4 talks about references. So references are important for our ADT converter, as you know. The primary reference is the internal reference, and the secondary reference is the external reference. And yes, I select the internal reference, which is 2.048 volt. I sample the 1.25 volt with that. The external reference, or at least a fraction of it. So this is again our bit test voltage, and I expect a certain voltage here. And if this voltage is not in range, I have a problem. I can still determine if it's the internal or the external reference which is broken while checking the second channel, right? If for the second channel there's also a failure, you can say it's the external reference, but you normally do not go that far. You would just say there's an error and discrepancy, and you would go to the safe state, basically. If everything drifts the same way, and here we have our temperature again, for example, then the reference, the external reference and the internal reference can drift the same way. The result would be the same. This needs to be avoided. That's why we have our temperature sensor. So then the ADC clock, also important. I mentioned this already in the beginning. So why is the ADC clock so important? Yeah, especially for the delta sigma converter. It's important because the filter, the decimation filter and so on, they are the response, the filter response is heavily dependent on the ADC clock. So if the ADC drifts, we can, in our case here, for example, we may not be able to guarantee our rejection ratio again, right? So the green area here means this is okay, it's in the specification. I think the specification is something like 86 or so. And if we have a plus minus 3% deviation, we can still be in the range. But if the clock drifts more than 3%, we get to the red area and we actually violate our specification. That's why we need to do that. How can we do that? The processor sends a SPI start command, conversion start. And once the conversion start command is sent, you can start a timer inside your processor, and the data ready pin, which is this one, tells you with an edge conversion finished. And this is also the time you stop your timer, you look at the duration, and then you can say, well, it's okay, A-to-D converter, it's in range, it's valid. Of course, the processor has also an internal clock where the timer runs from, and this can also drift. But here again, it doesn't matter what drifts. In processor, clock drift may also be a problem, and it would need also causing a shutdown at the end, right? So you identified an error. You cannot say which clock is now broken, but you know at least there is something wrong in your system, and this is actually what you want to know in a functional safety system. So then the second last diagnostic is the register content. And here I talked already about this very simple A-to-D converter. We have indeed only one ADC register here, and very good measure to actually test the register is just to read it back. So every time I write to the register, I read it back, and then I can be sure that what's been written is also actually inside the register. And if you have a more complex A-to-D converter, you may read entire register banks within a diagnostic test interval all the time. This could be quite busy on the SPI or on the I2C line. But for us here, we definitely change the configuration of register quite a lot, quite a bit. And we can also always be assured that it works by reading back the register. There could be another communication error if you want to read the communication, if you want to read the conversion register. So the conversion register means there is your data, your output code, right? And this is an unknown code. So you do not know what to expect. You didn't write to it, just read from it. And this is actually what you want to know, right? The output code. So what can you do to make sure this is really what's expected? So you can first do a repeated read. You can read 3 times, 5 times, do a majority voting. Then you can do a rationality check of the result. Does it really make sense? Can your loop jump from 4 milliamp to 20 milliamp within one conversion cycle? Is this possible? This is what you need to answer. And of course, the most important is the comparison with the redundant channel, right? So these are the important things you can do in order to make sure that the communication works. Of course, we have also A-to-D converter in our portfolio, which have CRC protection both ways, could also help. But in this case, it was not too important, and we could live without the CRC code at the end. So I think with that, okay, there's another one I remember very quick. Also very important is the environment. So here, the TMP 235 is used for the temperature measurement. I told you multiple times before, but I cannot really stress that point enough. So you get a great benefit with redundant channels. So you can easily compare in the 1 out of 2 at least. And this makes diagnostics simpler. but this comes with responsibility. So you have now really take care of the common cause failure. Make sure you shield, you do everything that there can be no influence which actually changes both channels in a bad way, same way. So then that the comparison cannot work anymore. This is important. And again, this needs to be assessed, at least in this case here, by the system integrator at the end, because he or she knows really how the functional safety application where our system is embedded should look like at the end. So with that, I'm already at the end of my presentation, and I would like to thank you very much for your attendance, and I hope you could learn this or that from this presentation. Thank you.
Thank you, Lars. Now let's move on to the Q&A sessions. We have already received a few. If you would like to ask anything, please use the Q&A button below. So the first question would be, can I use any type of components like multiplexers, ADC, etc., or components need to be rated with functional safety standards?
Mm-hmm. So very important is you can use any component from TI for functional safety. So this is a broad statement, but actually this is how it is. You just have to make sure it's safe. You have to make it safe. So there is there are the functional safety developed components, right? So they are really developed with functional safety in mind. They have full documentation, functional safety, and so on. It's a bit easier to actually get them on the board and get them certified. But for a multiplexer, this multiplexer, for example, as far as I remember, is not certified. This is not functional safety certified at all. But you can use it by addressing the defaults, right? Stuck of channels or open channels or does not switch. I mean, there are certain failure modes, and you can find on the TI webpage a multiplexer. You can actually search for multiplexer. Then I think there is at least one multiplexer which is functional safety compliant. No, functional safety capable. And then you open the document and you see the failure modes, and then you get an idea what failure modes can a multiplexer have. Then you actually address them. For example, my diagnostic 3 is stuck one of the channel. Here you can show how you can see how I actually cope with that fault type. But does this question the answer? Answer the question? I hope so.
Think that, yeah, I think it was a good answer. The next one would be, we got another question is, diagnostic circuit is generally one SIL level below the main channel, and even 2 SIL levels below if HST equals 1.
Yes, this is actually, this was also new to me. I talked to Truth about that, and yeah, this was the outcome, that generally the diagnostic is one less. So if you have a 1 out of 1 channel, then diagnostic is 1 CL lower. And if you are redundant, then you can reduce even 1 more.
Okay, we got another question. Can we rely to the failure rates databases, in example SN29500, or the responsibility for the decision shall remain with the expert during the safety assessment?
Can you repeat? I didn't get
the
question.
Sure. Can we rely to the failure rates databases, in example SN29500, or the responsibility for the decision shall remain with the expert during safety assessment?
Yeah, I mean, so what we do, we take the SN29500 and also the IC 62380, and this was also generally accepted by the certification bodies, no problem. So yeah, at the end, how can you how can you judge yourself whether this fit rate now is good or bad, right? You don't have maybe the data. Siemens took the time, the effort to build a database, and thanks God, made it publicly available, which is great. In terms of, I mean, you can order it from Siemens, but at the end, I think at some point we need to rely on the data. Yeah, I would say I would go for these standards.
How is EMC handled in such a system?
Yeah, EMC is one of the, it can be or is actually a common cause failure. So EMC would be on both channels the same way, and this needs to be avoided at system level. You cannot actually, you need to, under all circumstances, make sure that the EMC does not influence both channels the same way.
Okay. One more question, I think. What if one channel has a fault, but results are okay? And what if two channels have faults, but results of both channels are the same?
So if one channel has a fault and the results is okay, then this is okay because it's maybe a failure which is not dangerous, for example. So this is generally considered as okay, a single fault. Double faults, of course, not considered. So if there is, let's say, there are two channels and they are not common cause failures, but they both have the same issue and this results to the same error, then we are kind of out of the functional safety. So what we know is what we have is the HFT of 1, which means we can tolerate one failure, but the second failure is not covered anymore. So this means we are in trouble. If there are two independent errors in the channel which are not coming from common cause, and the probability is quite low, I would say, then this is not in the scope of the functional safety. Then there's a problem, yes. Hope this answers the question.
Thank you, Lars. I think we can have 1 more minute for another question. So is there a comparison of channels not enough? And why all the additional diagnostics?
Yeah, I think the 99% of comparison is already quite a big goal, comes quite a bit. So you may not need all the diagnostics implemented in this system. It can be less, but this really needs to be discussed with the assessor, right? With the TÜV or with the EXIDA, what diagnostic really needs to be on top of the comparison. So, so as far as I remember, the output code bit comparison was a must. So you remember this with the 0 1s and 1 0s. So even with the change in diagnostic test interval and with the comparison, the output code bit diagnostic was a must. But it's basically quite a simple implementation, so it was not too much of an effort.
Yeah, and we got 1 more question in the comments. Do passive components like resistors and capacitors are considered affect functional safety functions and validation?
Can you come again?
Do passive components like resistors and capacitors are considered affect functional safety functions and validation?
Oh, perfect functions? Perfect components?
Passive components.
So what are they considered?
Are considered affect functional safety functions and validation.
I'm not sure if I understand this question correctly.
Maybe it's a bit unclear, yeah.
So, I mean, maybe this answers the question. So, resistors and capacitors, you really need to choose them wisely. So you cannot really just take a resistor as you want. So, for example, metal film resistors, they have very interesting failure mode distribution. So there are 99% they fail open 99% and close only 1%. And if you build the resistors into your system, you need to consider that. So before you build in component, have a look at the failure mode distribution. So for the 99%, so you say, okay, this resistor, if this resistor goes open, what consequence has it for me? So if you, for example, have a resistor divider and the lower leg to ground opens, you have a full voltage to the next circuit, to the preceding circuit. This is a problem, right? So you may now think, okay, I can maybe put two resistors in parallel of this resistor divider, just when one opens, that the other is still having a certain voltage division. Whereas the higher leg, like the horizontal resistor of this resistor divider, if you say so, right? If this opens, then the lower resistor just connects the other circuit to ground, which could be a safe state. So have a look exactly how you use the components. Capacitors are more like 40-60, open, close, not as easy. But for example, the metal film resistors, they are quite thankful. And also, of course, you need to consider the PCB, right? So the component open, fail open can be also that the component gets off the board, right? This is a PCB problem then also.
Great.
This answers the question somehow.
Yeah. Thank you, Lars, and thank you everyone for joining. Questions will be answered in writing and be made available to all participants. Should you wish to watch the webinar again or share it with others, it will be available on demand soon. Finally, there is a short survey coming up, and we would be grateful if you could provide some feedback to help make our future webinars better. Thanks again, and have a good day.
Thank you. Bye-bye.
Bye.